Welcome to Week 11 Supply Chain Design course, Session 1. Topic for this session is routing and scheduling. Routing and scheduling belong to operative decisions which are required for running the daily transportation as well as production operations. The prerequisites are as follows. Typically, we are given known capacities that cannot be extended at shorthand so that resource scarceness cannot be prevented in some situations. Furthermore, detailed information about the demand to be fulfilled is available. The central challenge of operative decision making is now to match the demand with the available capacities on a daily basis. Here, two basic decision tasks has to be solved in isolation or in parallel. First, demand has to be assigned to resources, and second, schedules has to be set up. A schedule describes the sequence in which the assigned tasks are executed and at which starting points individual operations are initiated. The major difficulty is to ensure that the available capacities are not exceeded and that the resources are deployed at highest efficiency. A typical case for operative decision making is introduced in this session. In order to solve problems in a case study, this session introduces mathematical graphs as a tool for the representation of decision situation in a network structure. Additionally, the first insights into the algorithmic processing of graph data as the basic ingredients for decision making in network structures are provided. The consideration of complex restriction during the deployment of a resource is discussed by means of the so-called traveling salesman problem or TSP, in which the sequencing of operations to build a schedule for a resource is in the focus of decision making. The integrated consideration of assignment and scheduling or sequencing decision problems under limited resource availability is addressed in this session in the context of capacitated vehicle routing problem or CVRP. In production planning, a short introduction into the scheduling of the production machines is given, and this session will introduce a way of computing optimal and heuristic production schedules. Now let us read a case study of Red Sea bus travel. The leading actor of this chapter is Christina. She had just completed her study program, equipped with a recently acquired bachelor degree in certifying her successful studies in leisure and tourism management. She wants to achieve some job experience abroad. So she applies for several jobs in the well-known Hurghada Red Sea area in Egypt. After several interviews, she finally got a job at Red Sea Bus Travel, or RSBT. This company offers transport services in the Hurghada region. International travel agency book RSBT service operations in order to ensure that their tourists are moved to their preferred holiday region. At her first working day, Christina is assigned to the planning and dispatching office of RSBT in downtown Hurghada. After several complicated years of business due to a lack of tourists, RSBT has detected an increasing number of bookings from travel agencies, but also from individual customers. These bookings can be classified into the following four categories. First, limousine services or LS. sightseeing tours or SST, airport arrival transfers or AAT, and finally airport departure transfer or ADT. RSBT or Red Sea Bus Travel receives all booking at shorthand, for instance, on the day before the transport service is executed. Service transport processes have to be set up in order to cover customer demand. RSBT operates a fleet of minibuses of different sizes and also has qualified drivers. Assignment of bookings to buses has to be decided, and for each bus, the daily schedule has to be determined. Christina's task is now to analyze the four products: LS, SSD, AAT, and ADT, and to make suggestions how the day-to-day deployment of the available buses, which are the available resources, must be carried out in order to use these resources in the most efficient manner while all booking requests are fulfilled. Having accompanied several transport services during her first week at RSBT, Christina has identified the core planning challenges in the four business sectors. First, for LS, limousine service, what is the shortest or quickest path through the local street network to travel from the limousine service headquarters to the airport? How can this path be identified? For the second, sightseeing tours, in which sequence should all the nice places be visited so that visitors have enough time to enjoy their leisure time in the hotel? And for AAT, what is the minimal travel distance to bring all inbound passengers associated with an inbound flight to their hotels? What is the minimal number of required buses? And for ADT, airport departure, which bus should pick up which guests from which hotel in order to take them to the airport on time if customers do not accept a pickup more than 5 hours earlier than their scheduled flight departures. Christina is now looking for suitable planning models for the four types of transportation service situations. Her intention is to make the determination of the processes traceable, but at the same time, she wants to ensure that efficiency of the deployment of resources is as high as possible. Before solving the case study, we need to understand routing and scheduling that belong to operative decisions which are required for running the daily operations. There are thus similarities between the two that both assigned orders can be jobs or delivery orders, and based on resource requirements can be production or delivery time. Machines or vehicles do the assignments. The figure in the current slide shows that both machine scheduling and truck routings minimize finished good inventory by reducing idle time of products in final product storage. In explaining mathematical graph in our current slide, we back to our case study where Christina evaluated all four products. She first turns towards the LS business or limousine service. In the first step, she is asking the booking department for data about the usual as well as about the most frequently booked relations for limousine transports. Her survey results in the observation that 6 locations contribute to the daily LS operations. The fare for an LS booking is calculated based on travel distance between the book pickup location and the book delivery location. From discussions with LSBT customer care manager, Christina has learned that there are several complaints from customers who think that they have to pay too much since drivers do not follow the shortest travel route. Christina wants to find out if these complaints are justified, and she decides to have conversation with some drivers. After her interviews, she was convinced that the complaints were not justified. All of the complaints are as a result of a misunderstanding. The infrastructure in the area is quite different from the typical European street network. Since all hotels have been built around the populated downtown area, there are only streets that connects the biggest hotels. That means going from a pickup point to a delivery point often requires a visit to several hotel places. The street network is significantly less dense than in a typical European city, and felt detours are needed when retraveling in the area. In order to provide more transparency for customers and in order to instruct the limousine drivers, Christina decides to create a list for each pair of pickup and delivery point combinations. She wants to add the shortest route to each pair to inform the drivers and the corresponding travel distance to inform the customers. In the first attempt to compile the desired list, Christina collects data from street map. She marks the set location A to F as shown in our slide. Furthermore, she looks for streets connecting these locations. Whenever she finds out that there is a street connecting a hotel with the airport, or the airport with a hotel, or a hotel with another hotel, she connects the original location with the terminal location by an arc. That is, an arch represents an existing street connecting these 2 points, and the arc direction indicates the direction of the travel. Finally, she appends the length given in kilometers of such streets or section between 2 points. From the compiled simplified map, she learned, for example, that there is a street that goes from A, Riverside, the fisherman village, to D, Mermaid's Inn, but in this street cannot be used to go from D to A. The length of the street section from A to D is 3 kilometers, but what is the distance a trip from E to F? Christina is looking for a comfortable method to determine the least travel distance by solving the shortest path problem, or SPP, between a pair of pickup and delivery locations not directly connected by an arch. When relate the previous case with figure in our current slide, we can see that in order to determine the shortest travel distance, Christina needs to build a mathematical graph to describe the travel network structure. The networks consist of some points of destinations as well as road transports networks to connect between 2 destinations. In a mathematical graph, these points are represented by nodes and the road by arcs. If the arcs hold some information, for instance transportation distance, such a graph is called weighted mathematical graph. In our slide, in order to connect all destinations optimally at minimum travel time and costs, then Christina needs to determine round trips of buses that contain exactly 1 visit for each location, contained in a given list of sightseeing objects. Christina examines the sightseeing tour, or SST, situation, and she finds out that there are some similarities with the shortest path identification problem in finding shortest distance based on available cost or distance information. First, the sightseeing tours challenge is also lives in a network structure. Second, for a given list of points of interest, a connecting path in the given network structure is required. Third, also in the sightseeing tour situation, a path with minimal length is searched. However, Christina discovers an important difference between LS, limousine service, and sightseeing tours or SST situations. In the LS challenge, only the starting as well as the terminating node of the requested ST path is given. There are no requests to visit other nodes. In contrast, the necessity to visit all locations contained in the aforementioned list of points of interest is postulated. For this reason, Christina concludes that the Dijkstra algorithm is not sufficient tool to solve the SST challenge, since this algorithm does not provide the opportunity to manage the constraint that each node contained in the network is visited exactly once. In this section, we accompany Christina while she learns how optimization problems on network structures can be solved, if restrictions on a solution must be considered. She read from her lecture notes that the traveling salesman problem, or TSP, represents the basic decision task of many vehicle deployment problems. It is quite similar to the shortest path problem, since also in the TSP it is necessary to fulfill a transportation task in a network structure with minimal resource utilization. Let's see the figure in our slide. There are three destination points need to be visited by a bus of Red Sea Bus Travel Company. The numbers show the travel distances between two connected locations. For instance, the distance between A and B is 2 miles. Between A and C or vice versa is 1 mile. Minus sign signify that there is no distance between the same destination points, in this case between A and A, B and B, or C and C. In that sense, the TSP is distinct from the shortest path problem, since all nodes in the networks have to be visited but no node is allowed to be visited more than once, which means that each available node must be visited exactly once. There is also a distinct node called the starting node, or the depot from which the traveling salesman starts his journey and to which he returns after all other nodes have been visited exactly once. The salesman wants to keep its total sum of travel distances between the visited nodes as small as possible. Finally, Christina summarizes these findings and transfers her finding to the SST challenges. She is convinced that the TSP represents exactly the SST problem setting. There is a set of nodes given, and these nodes, in the SST case, the given points of interest must all visited by a vehicle, but the length of the travel path must be minimal. Christina continues to read the instructor's notes. Without going into details, she understands that the TSP, or traveling salesman problem, can be modeled as a linear program, but that it is impossible to apply the standard approach for linear programs, which is the simplex algorithm, to solve this model. For this reason, her lecture notes proposes to apply other decision support methods, which are called heuristics. Now Christina's attention is awakened and she decides to study in detail the information given in the course material about the TSP, its modeling, and the heuristic model solving techniques. First, Christina wants to understand the case that motivates in the current slide. The outline of the case study is as follows. A sales representative lives in Hamburg. Each week, she had to visit the remaining 13 cities in the northern Germany. She wants to visit all these cities with one trip. If necessary, she will have an overnight stay in one of the cities. In order to show up at the retail outlet store of her company, and according to her contract with this company, she has to pay for the fuel cost on her own. In order to keep the fuel expenses as low as possible, the sales representative is searching for a least distant round trip that starts in Hamburg, terminates in Hamburg, and visits all remaining 13 cities exactly once. Christina continues to learn about the case. The sales representative, which is in the role of the traveling saleswoman, can travel directly from each given city and each given other city as indicated by the graph in our figure. Indicated by the graph in our slide. Such a graph in which each node has a connection to each other node is called a complete graph. At first look, such a network structure seems to make the determination of a round trip easier than the determination of a round trip in a general graph where not all destination points are completely connected with other destination points, and thus detours on the way from one node to another node are not necessary. For example, there are two feasible routes that start and end in Hamburg. They are Hamburg and then Munich, Berlin, and back to Hamburg, or Hamburg to Berlin, then to Munich and back to Hamburg. We can enumerate all feasible routes at a higher number of cities which start and end at Hamburg. For instance, in our slide, 3 cities have 6 feasible routes to be evaluated in order to find the shortest route. First, Hamburg, Munich, Berlin, Frankfurt, and Hamburg. Second route, Hamburg, Munich, Frankfurt, Berlin, and back to Hamburg. The third route, Hamburg, Berlin, Munich, Frankfurt, and back to Hamburg. And the fourth, Hamburg, Berlin, Frankfurt, Munich, and Hamburg. And the fifth, Hamburg, Frankfurt, Munich, Berlin, and back to Hamburg. Finally, the last route is Hamburg, Frankfurt, Berlin, Munich, and back to Hamburg. This slide provides a data of how many feasible routes at different number of nodes, and we find that the development of the number of feasible routes are exponential and therefore not possible for us to find an optimal solution by enumerating the routes. For instance, here, for one visit node, we have only one route, from Hamburg direct to Munich. For 2 visit nodes, from Hamburg to Munich and Berlin, we have 2 possibilities. For 3 visit nodes, we have 6 routes, as mentioned in our previous slide. But 4 visit nodes needs 24 routes to be evaluated. And for 20 visit nodes, we have more than 1 million, even more than 1 billion feasible routes. And we have to pick one that is the best. So, can you imagine now, for instance, if we have 15,112 nodes to be visited Can you count how many feasible routes are there? There are two main methods to solve traveling salesman problem. The first is heuristic, and the second is optimization. Heuristic methods in algorithm approach to solve a decision made by exploiting a rational strategy of planning without mathematical proof that the proposed or returned feasible model solution cannot be dominated by another feasible solution or a non-optimizing algorithm. In contrast, an algorithm for which the return solution proposal is proven to be a minimal or maximal is called an exact or optimization algorithm or approach. The simplex algorithm is an example of an exact algorithm, and also branch and bound. Other types of heuristic methods are meta-heuristic, such as simulated annealing, taboo search, and genetic algorithms, or GA, that mimic natural behavior to solve TSP even without having known about the TSP model. The methods are able to find feasible solution at a relatively shorter time than heuristic, but cannot always find an optimal solution. For optimization, we have branch and bound that uses integer programming to find an optimal solution. Branch and bound, or BB, use a tree search strategy to implicitly enumerate all possible solutions that give to a given problem, applying pruning rules to eliminate regions of the search space that cannot lead to a better solution. There are three algorithmic components in branch and bound that can be specified by the user to fine-tune the behavior of the algorithm. These components are the search strategy, the branching strategy, and the pruning rules. Heuristics are incorporated into model solvers in case no exact algorithm is available, or if the processing time provided by an exact algorithm are expected to be prohibitively long. Since the processing time for solving relatively small instances of a TSP is in general quite long, it seems to be reasonable to think about a heuristic approach for the TSP. The method that we discussed in this session is greedy nearest neighbor. It was proposed by Joben and Sebastian in 1998, describe a quite intuitive approach for the construction of a Hamiltonian path. The central idea is to consecutively insert the nodes after the last visited node until all nodes are contained in the path. A Hamiltonian path is created. This approach is also known as a nearest neighborhood heuristic. Greedy heuristic is very simple. It starts with an empty path. For the first step, the starting node, in our example node number 1, is inserted. Next, the node with the shortest distance from the starting node is inserted just after the starting node. This path extension is iterated until no further node is remaining. This path construction procedure follows the rational strategy to keep the additional travel distance associated with serving the next customer after the previously inserted customer as low as possible. Therefore, the applied rational strategy can be characterized as greedy. Consequently, this construction heuristic is named greedy construction procedure. A major shortcoming of the greedy construction procedure is its myopic insertion strategy. After all nodes have been inserted into the node sequence, it is necessary to return to the start node. The travel distance for the return to the depot is not considered in the calculation of the additional travel distance to serve the next customer. Consequently, the greedy strategy cannot be proven to return the shortest possible Hamiltonian path. However, it returns a first Hamiltonian path. Now let's work with the current example. We have a Santa Claus who wants to visit 4 children at different locations. The Santa wants us to help him to find a shortest route and therefore enables him to deliver Christmas present on time. Let's work with the example. This pseudocode represents the greedy construction procedure that consists of initialization phase A, iteration loops P to I, and termination phase J to L. During the initialization phase, the travel distance is set to 0, and the first node in the path is set to the starting node equal to 1, or home of the salesman. The iteration counter k is initialized. Exactly one node is appended to the already existing partial path in each iteration. Each iteration starts with a check whether there are still unblocked columns. Such an unblocked column represents a node that has not yet been appended. Among all unblocked columns, that is available nodes, a node's DSD or destination or test with the least distance D from start to destination, start, test, from the last appended node start is chosen, that is C. Afterwards, the so far traveled path length L is increased by L start test at D number. Next, the row as well as column associated with test is blocked, that is E. The recently selected node test is appended to the already existing partial path F, and test DSD will be set to the latest inserted node, that is G. The iteration counter is increased by 1, that is H, and the procedure jumps back to the beginning of the loop, that is I. In the case of no further unblocked column being available, the path will be closed. For instance, the arc from the last appended node to the starting node is selected, that is J, and the travel distance is updated, that is K. Now let's work with one example here. I will start using the greedy algorithm to solve this example. Alright? First, I would like to find here the shortest distance from point number 1, or from the start point 1. And I found number 6. Here is the closest from 1. And therefore, I would cross this number 6 column. And then from 6, here, let's find number within this row that is the smallest. And I found that is number 1, but 1 already crossed. And then the second should be number here I found number 5. Is it correct? Yeah, I think so. It's number 5, right? So here, number 5. And I can cross here. So 1, 6, and then 5. And then from 5 to, let's find because once already crossed, then we have to exclude this also. From 5 to 7, and then I cross 7, and then I put here 7. From 7 to here, from 7 to 12, alright? Is it correct? Yeah, to 12, I think. To 12. And then from 12 to 9, then we cross 9. From 9, and then 2 to 2, right? To 2. Then we cross here number 2. Then from 2 to 3. Yeah, to 3. And then from 3 to should be to 13, right? And 13 to 14, right? And then from 14 we go to 4. From 4 we go to 4 to 10, right? And then from 10 we go to 11. Is that correct? Yeah, to 11. From 11 we have only here only one left, that is to 8. And then from 8 back to 1. So here is the sequence of visiting 14 location. And you can check the result by using this figure. From 1 to 6, and then 6 to 5, and then from 5 to 7. Okay, let's check. Yeah, at least for the first 4 destination, it is the same with this figure. Okay, now we go to a vehicle routing problem. Before going into vehicle routing problem, if we look at these greedy heuristics, the phenomenon observed here refers to a general shortcoming of heuristic search for solutions if several constraints have to be considered while trying to optimize the objective function. It is either trying to fulfill the optimization property of, or it is trying to achieve feasibility of the generated solution proposal. At first glance, it seems that the greedy construction procedure fails for the TSP, but it is worth getting a first feasible Hamiltonian path, since it is possible to improve the objective function using so-called improvement heuristics that modify the initial feasible solution. These improvement heuristics focus on the minimization of the objective function value but also keep the feasibility of the modified solution. You can further follow the improvement heuristic from our textbook in order to get through the algorithm. In the next slide, we will continue with vehicle routing problem for both uncapacitated and capacitated. Let's back to our case study. Christina turns to the next large business area, which is the local transfer of inbound tourists. RSBT or Red Sea RSBT, the touring company, provides this service to international travel agencies. These agencies sit the company provides the service to international travel agencies. These agencies sell all-inclusive travel packages to customers. Such a package includes, first, a return flight tickets from the selected origin airport to Hurghada International Airport, accommodation in the selected hotel in the Hurghada region, including breakfast or half board or full board or all-inclusive food and beverage. The third is transfer on day of arrival with a pickup at the airport and a drop-off at the selected hotel. Transfer on the day of departure from the hotel to the airport. Christina finds out that RSBT or the company generates a significant amount of income from the transfer services, but the profits are quite small. She discusses this observation with the responsible division manager. The manager mentions that the transfer of incoming passengers, that is AAT or airport arrival transfer, is easier to plan than the transfer of outbound passenger of airport departure transfer. Since in the airport departure transfer, setup pickup times at the hotels have to be considered. In the AAT or airport arrival transfer setup, such time windows do not play any role. Christina and the manager commonly decide that for the reasons of the time, they have to separate the AAT from the ADT operations planning. Furthermore, they decide to analyze the AAT setup first. Since Christina is not familiar with the AAT business, she asked for an example in order to get an insight into the preparation and execution of some AAT services. The manager selects a certain day from the last month. On that day, there was one evening flight that carried overall 29 passengers to the airport of that city. Different travel agencies have booked the corresponding AAT service at that company. Overall, 14 hotels have to be served. The number of passengers to be brought to a hotel varies between 1 and 4. The hotels are distributed around the airport. Next, Christina wants to know how the passengers are transported to the hotels. She learns that 4 minibuses are available to fulfill the AET service or airport arrival transfer. Each minibus offers 10 passenger seats. All minibuses start their operations from a large parking lot at the airport. From there, a minibus moves to the exit of the airport arrival hall where the passengers to be served enter the minibus. Next, a minibus goes to the requested hotels where passengers are dropped off. Within a service trip, a minibus regularly visits one or more hotels before it returns empty to the parking lot of that airport. The AAT managers tell Christina that he has the feeling that the performance of the AAT or airport arrival transfer operations is quite low. In particular, he thinks that the distances traveled or therefore trip durations are quite high. As a consequence, the number of deployed vehicles seems to be quite high. overall AET operation seems to produce unnecessary travel cost, fuel cost resulting from detours, as well as personal cost for the drivers. In order to demonstrate this, the AET manager produces some trips that is executed by the 4 vehicles, and it is found that the total travel distance is at 873.7 kilometers. From the story, we can conclude that vehicle routing problems allow more than one departure from the same origin, and each of those vehicles has its capacity limit, and with their capacity limits, the vehicle routing problem needs to meet the demand. Thus, there are 2 tasks here. First, to determine the number of vehicles, and the second, payload per vehicle. There are different variations of VRP subject to specific constraints that an organization is facing. The objective function of VRP can be time, distance, and cost, and also penalty, that to be minimized. Can be solely or in combination among those 4 performance indicators. The constraints include fleet size, individual vehicle capacity, or depot of reference. Customers may in terms of demand size, time windows, or the number of nodes. Similar to TSP, the road networks are represented by vertices that stand for customer and depot, and arcs that stands for roads. The number of depot can be single or multiple, which is another distinction of vehicle routing problem or VRP against TSP or traveling salesman problem. Finally, additional constraint can be the number of working period for drivers as well as shift and break requirements for drivers. There are several solution methods of VRP. In general, the solution methods are divided into 2 streams, heuristic and exact methods. For heuristics, 3 methods of saving heuristics that we will discuss in this session, iterative improvements, and meta-heuristics are known based on experimentation, evaluation, or trial and error methods. On the other hand, exact method based on mathematical modeling that can be solved by using branch and bound. Branch and bound with additional cutting planes and set covering based algorithm, which is basically cutting planes method. For saving algorithm, the idea is that to find saving from combining 2 or more destinations to be visited by single vehicle. Then first, we select any nodes as the depot node, node number 1. And then start computing the saving. The saving, that is Sij, saving because of connecting I to J. Then we compare between visiting the 2 nodes using 2 vehicles and only once visiting those 2 using a single vehicle. Then the saving can be calculated as follows, that Sij equal to C1I, meaning that cost because of using a vehicle to travel from 1 to I and back, and C1J, that is cost, travel cost because of visiting J from 1 from depot and back, minus Cij. Cij is the cost of traveling from I to J. And then we rank the savings from largest to smallest. Finally, starting at the top of the list from larger subtours by linking appropriate nodes I and J, and stop when a complete tour is formed. Okay, let's take an example, these 2 graphs here. Alright. Okay, we have two options: visiting ing separately by using two vehicles or using only a single vehicle. And then we can calculate if the travel distance is here is 6, here also 6 from I, and here is 7, and then here is 7, and the total travel is that 6 plus 6 plus 7 plus 7 equal to 26. However, if we travel here directly from 0 to I to J and back, and then we have here 6, here we have 7, and we have 8, and therefore the distance is shorter at 21. Alright, so we have saving about so we have saving about 26 minus 21 equal to 5, and therefore C1I, it is 6, right? And then C1J, it is 7, and then again minus 8, right, equal to 6 plus 7, it is 13, minus 8 equal to 5. It is equal to this number, 26 minus 21 equal to 5. Okay, this is one example how to calculate the saving. And we can work with this example. All right, let's start with calculating saving of these networks. Here we have a table of distance metrics. For instance, traveling from 0 to 1 cost 5.5, or maybe the distance is 5.5 miles. 0 to 2, it is 9, right? Similarly, we can also write here 24.12.4, 8.3, and 6.4. Here also we have 8.9, 12.1, 11.5. Here we have 10.6, 9.1. Here also we have 9.9. Alright. Now we have to sequence the travel and to determine how many vehicles needed to visit all these 5 points of destinations. Okay. At this slide, we try to calculate the saving. For instance, here, saving by combining 1 and 2 all together by using a single vehicle. Then we back to our table here. Visiting from 0 to 1, 5.5. From 0 to 2, it is 9. And then visiting from 1 to 2, it takes 2.3. And therefore, we can find here 5.5 plus 9 minus 2.3. 5 5.5 plus 9 minus 2.3 equal to, okay, let's calculate 14.5 minus 2.3. So we have here 2, here we have 14 is 12.2. Oh, let's check it is correct or not. Yeah, 12.2. And we do the same by combining 1 and 3. By combining 1 and 3, we have here 0 to 1, 5.5 plus 12.4 minus 8.9. Here we have 17.9 minus 8.9, and then we have here 9.0. Yeah, we have here 9. We do the same for all possible connection here, and then we have the following number. We have, by connecting directly from 1 and 4 into one vehicle. Now let's compare our calculations, the total resistance from our calculation using saving method and by using FIFO, first in, first out. FIFO assume that the first destination point should be the shortest distance from point 0, that is the location of depot. From the previous slide, we know that number 5 is the shortest from 0, and therefore from 0 we go to 5, and then from 5 go to where? Let's say here from 5 the least distance should be go to number 4, right? From 5 to 4, and then from 4 to, and then we from 4 we have to check which next destination that has the least distance with 4, and then we have here number 3. It is 4.7, right? And then from 3 to where? From 3 to 2, right? Because we have already covered 5, and then 4, and then 3, and then now is from 3 to 2 here, and then from 2 to finally to 1. Okay, let's check. Yeah, 5, 4, 3, 2, 1, and then back to 0, and the distance is, the total distance is 31.6. Definitely it is higher than 37.2 found by using saving method. So how come that FIFO is better? But sometimes using this heuristic method we can get worse solution and sometimes even better solution depending on which the first entry point in our networks. Because here in heuristic method we choose that the entry point is 3, and then we start calculating from 0 to 3, right? And then from 3 to where? To 4, because 4 here has the higher saving if we combine directly with 3. And then from 4 to 5 here, because here the connection has 11.5 saving. From 5 then to 2 here, 5 to 2, right? And then from 2 to 1, and then finally to 0. Okay, why from 5 we connect to 2? Because if we connect 5 for instance to 3, for instance here 3 already passed. If we connect 5 with 1 here, for instance, but 1 has the lower saving as compared to connecting 5 to 2, and therefore the total distance is 37.2 kilometers, which is not better than FIFO, first in, first out. Another application for saving algorithm is capacitated vehicle routing problem, In the previous vehicle routing problem, we do not have any limitation about our vehicle capacity, but here we have capacity limit. In this example, we have 6 destinations to be visited, but we have to determine how many vehicles will be used and how much or how many load should be put into each vehicle. And then we have the following. I is the index for customers and K is the index for vehicles. And customer request, that is QI, that is customer request at index I. And driving cost to connect or to travel from I to J, that is CIG. And the capacity vehicle K, that is QK. Right? What is given? We have a demand or customer request from customer number 2 at 2 units, customer number 3 at 1 unit, customer number 4 1 unit, customer number 5 at 3 units, customer number 6 at 1 unit. So here we have customer number 2 here, customer number 3 here, number 3, customer number 4, customer number 5, and customer number 6. That is the demand for each customer. And the number of vehicles is 2, and each of those vehicles has capacity limit at 5. Okay? Now let's assign a vehicle to which destination. Using saving method, so saving algorithm that we have already known in the previous slide, we have calculated, for instance, combining 2 and 3, we have saving 5. 2 and 4, we have 10. 2 and 5, we have 1, and so on, alright? Similarly, for the left list, we have combining 2 and 4, we have 10, saving. 5 and 6, we have 10. 3 and 9. 3 and 6, we have 9, and so on. Using this saving data, we will try to cluster which location served by which vehicles. The first entry, again, because it is heuristic, you can freely determine which entry among this list that will start your computation. Here we choose S24, and therefore in S24, yeah, it is reasonable because S24 has the highest saving in this case, and then S24 equal to 10. Therefore, the tour begins at customer 2 and is continued by customer 4. The next combination possibly is 3 and 4. Okay? Here we have 3 and 4. This and 3 and 4. Because after connecting 2 and 4, and then 4 need to be connected by another destination, that is here is 3. Okay? And then the connection will be 2, 4, and 3. Having done this, the tour can be completed with S3 and 6. And then after from 3, then 3 goes to customer number 6. 6 is the last station for vehicle K because the capacity is 5. And we can see that by picking up an order from customer number 2, 4, 3, and 6, 2, 4, 2, customer number 2, order is 2, plus customer number 4 and 3, each is 1 unit, and plus customer number 6 at 1, and therefore it is 5, and therefore 5 is the maximum payload that can be carried by each one of these vehicles, and the rest of the loads will be carried by vehicle number 2 at 3 units. And then vehicle number 1 routes would be from depot to customer number 2, number 4, number 3, and number 6, while vehicle number 2 only carry product from customer number 5 and back to depot. Alright, so this all how to compute the capacity vehicle routing problem. So you can see now the difference between CVRP and VRP. In VRP, we don't care about the capacity limit of our vehicles, but in CVRP, we care about that. And this is more, therefore it is more realistic. However, it is not the only version of CVRP, but we have also VRP with time windows, meaning that in addition to sending product or to pick up product from a particular location, we have to consider also the time windows. For instance, a vehicle cannot arrive during late night because the warehouse or the facility or factories, for instance, or shop, store, or supermarket already closed. So it is not possible to arrive at that destination during late night. And even not only with time window, not only with capacity limit, but also with distance limit. So for instance, a particular vehicle, because of travel restriction, mostly during this pandemic, cannot travel for more than 20 or 30 kilometers from its original point of departure. All right? Okay. In the next session, we will continue with production scheduling.